December 7th, 1972, something extraordinary happened. The crew of Apollo 17, the last manned mission to the moon, captured what would become the most reproduced photograph in human history. They called it the Blue Marble. But here is the part nobody talks about. When astronaut Eugene Cernan looked out of that tiny window and saw Earth floating in the absolute blackness of space, he reported something deeply unsettling. He said he could not tell which way was up. He could not tell which way was down. The Earth was just there, suspended, with no reference, no anchor, no direction. He described a moment of pure disorientation that shook him to his core. And this was not some amateur floating in zero gravity for the first time. This was a man who had walked on the moon, a man trained by NASA for years. And yet, in that moment, staring at our planet from 250,000 miles away, he realized something that most of us never think about. The concept of up does not exist. It never did. We invented it. Our brains created it as a survival mechanism, and the moment you leave this thin shell of atmosphere wrapped around our tiny rock, the illusion shatters completely. Now I want you to pause for a moment and think about something. Right now, as you are watching this, you feel like you are sitting upright. You feel like the sky is above you and the ground is below you. You feel like up is a real direction, a real thing, something as fundamental as time itself. But what if I told you that someone on the exact opposite side of the Earth right now feels exactly the same way, and their up is pointing in the completely opposite direction from yours? What if I told you that up is not a direction at all, but a feeling, a sensation created by your inner ear, a trick your brain plays on you every single second of every single day so that you do not go insane? What if I told you that in the vast majority of the universe, the concept of up is not just irrelevant, it is physically meaningless? It does not apply. It cannot apply. The laws of physics do not recognize it. And here is where it gets truly mind-bending. When you watch a rocket launch, you see it go up, straight up into the sky, and your brain tells you, yes, it is going up, it is going to space, space is up there. But that rocket is not going up. It physically cannot go up, because up does not exist as a direction in space. What that rocket is actually doing is something far more elegant, far more complex, and far more beautiful than simply going up. And by the end of this discussion, you will never look at the sky the same way again. You will never think about space the same way again. And most importantly, you will understand something about the nature of reality that 99% of people will go their entire lives without ever grasping. We are going to go deep today. We are going to explore why direction is an illusion, how Einstein proved that there is no such thing as a fixed reference point in the universe, why gravity is not actually a force pulling you down, but something far stranger, how quantum mechanics destroys the very concept of position itself, and why the universe at its most fundamental level has no up, no down, no left, no right, no forward, no backward. We are going to journey from the surface of this planet all the way to the quantum foam of space-time itself. And along the way, everything you thought you knew about where you are and which way you are facing is going to dissolve. If this kind of deep scientific exploration excites you, if you are the kind of person who wants to understand reality at its deepest level, then do me a favour right now. Hit that subscribe button, press the like button, and drop a comment below telling me what you think up actually means. I am genuinely curious to hear your answers before we tear the concept apart. Because trust me, by the end of this, your answer will change completely. Let us begin with something that seems so obvious that no one ever questions it. You are sitting or standing somewhere right now, and you feel the ground beneath you. You feel weight, you feel a pull toward the earth. And your entire life, every single moment of your existence, you have interpreted this feeling as down. Down is where gravity pulls you. Down is where things fall. Down is the direction of the floor, the ground, the centre of the earth. And up is the opposite. Up is where the sky is. Up is where birds fly. Up is where the stars are. This seems so fundamental, so basic, so obviously true, that questioning it feels almost absurd. But science is in the business of questioning the obvious. And when we question this particular obvious thing, reality starts to crack open. Let us start with a simple thought experiment. Imagine you are standing in New York City. You feel gravity pulling you down toward your feet. Now imagine someone standing in Sydney, Australia at that exact same moment. They also feel gravity pulling them down toward their feet. But here is the thing. If you could draw a line from your feet through the centre of the earth and out the other side, that line would point roughly toward Australia, which means the person in Sydney is standing upside down relative to you. Their down is pointing in the opposite direction from your down. Their up is pointing in the opposite direction from your up. And yet, they feel perfectly normal. They do not feel upside down. They do not feel like they are hanging from the bottom of the planet. They feel exactly the way you feel. Completely right side up. So who is actually right side up? Who is actually oriented correctly? The answer is both of you. And neither of you. Because up and down are not absolute directions. They are not carved into the fabric of reality. They are local phenomena. They are relative to where you happen to be standing on the surface of a sphere. And this is the first crack in the illusion. Up is not a direction in the universe. Up is simply whatever direction happens to point away from the nearest massive object. It is defined entirely by gravity. And gravity is local. It changes depending on where you are. There is no cosmic arrow pointing up. There is no universal up. There is only your up, which is different from someone else's up, which is different from an astronaut's up, which eventually becomes no up at all. Now let us go deeper. Why do you feel up and down in the first place? The answer lies inside your head, specifically inside your inner ear. There is a structure called the vestibular system that acts as your body's orientation sensor. Inside this system, there are tiny chambers filled with fluid, and within that fluid, there are even tinier calcium carbonate crystals called otoliths. These crystals are denser than the fluid around them, so when gravity acts on them, they settle toward whatever direction gravity is pulling. Your brain detects which way these crystals are shifting and interprets that as down. This is how you know which way is up even with your eyes closed. This is how you maintain balance. This is your body's built-in accelerometer. But here is the critical point. This system does not detect direction in any absolute sense. It detects acceleration. Specifically, it detects the acceleration due to gravity. And as Einstein showed us more than a century ago, there is no way to distinguish between gravitational acceleration and any other kind of acceleration. If you were in a rocket accelerating at 9.8 meters per second squared in the depths of space, far from any planet or star, your vestibular system would tell you that down is behind you, in the direction opposite to the acceleration. You would feel weight. You would feel gravity. But there would be no planet beneath you. There would be no massive object pulling you. Your sense of up and down would be created entirely by acceleration. And this is Einstein's equivalence principle, one of the most profound insights in the history of physics. Gravity and acceleration are indistinguishable. Your body cannot tell the difference. Your sense of direction cannot tell the difference. And this means that your feeling of up and down is not detecting some fundamental feature of the universe. It is simply responding to local acceleration, whatever the source. This has profound implications. It means that if you were floating in space, far from any source of gravity, with no acceleration acting on you, your vestibular system would have nothing to detect. The otoliths would float freely in their fluid. Your brain would receive no signal about which way is up or down. And in fact, this is exactly what happens to astronauts. When they reach orbit and experience weightlessness, their vestibular system goes haywire. The otoliths float. The fluid in the semicircular canals behaves differently. And the brain, which has spent an entire lifetime relying on this system to know which way is up, suddenly receives contradictory or absent signals. The result is space adaptation syndrome, a very real medical condition that affects roughly 60 to 80% of all astronauts during their first few days in space. The symptoms are fascinating from a scientific perspective. Nausea, vomiting, spatial disorientation, perceptual illusions. Astronauts report feeling like the room is spinning. They report feeling like they are falling. They report moments where they cannot tell which way they are facing even with their eyes open. Some astronauts report that whenever they close their eyes, they feel like they are tumbling uncontrollably. This is your brain desperately trying to compute up and down and failing, because in orbit there is no up and down. The concept does not apply. The signals that your brain has always used to determine direction are simply gone. NASA has documented this extensively. In the early days of the Space Shuttle program, astronauts were studied carefully to understand how the brain adapts to the loss of gravitational reference. What researchers found was remarkable. After about 3 to 4 days, most astronauts' brains completely rewire their spatial processing. They stop trying to find up and down. They start navigating purely by visual reference, by memory, by spatial awareness, independent of gravitational direction. Their brains essentially abandon the concept of up and down altogether. And when they return to Earth, many astronauts report a period of readaptation where they have to relearn that down exists. Some drop objects because they unconsciously expect them to float. Some stumble because their balance system takes time to recalibrate to gravity. This tells us something incredibly important. Up and down are not fundamental. They are learned. They are computed by a brain that evolved on the surface of a planet with gravity. And the moment you remove that gravity, the concept evaporates. It is not that up and down become difficult to determine in space. It is that they literally do not exist there. Asking which way is up in orbit is like asking what colour is the number 7. The question does not have an answer because it does not apply. Now let us talk about what actually happens when a rocket launches, because this is where one of the biggest misconceptions lives. You watch a launch, the countdown reaches 0, the engines ignite, and this magnificent machine rises off the pad, climbing what appears to be straight up into the sky. And in your mind you think, it is going up, it is going to space, space is above us, and the rocket is going there. But this picture is almost entirely wrong. First, let us talk about what happens in the first few minutes of a rocket launch. Yes, the rocket initially moves perpendicular to the ground, straight away from the launch pad. But this phase lasts only a very short time. Within about 30 seconds to a minute after launch, depending on the vehicle, the rocket begins what is called a gravity turn. It starts tilting. Slowly at first, then more and more, the rocket pitches over from vertical to nearly horizontal. By the time it reaches orbit, the rocket is moving almost entirely sideways relative to the Earth's surface. It is moving parallel to the ground, not away from it. Why does it do this? Because getting to space is not about going up. This is the fundamental misconception. Space is not above you in any meaningful way. Space is about 100 kilometers above you, which sounds like a lot until you realize that the speed you need to stay in space is not vertical speed, but horizontal speed. To reach the edge of space, you need to go about 100 kilometers up. But to stay there, to actually orbit, you need to be moving sideways at approximately 28,000 kilometers per hour. The altitude is almost irrelevant compared to the speed. If you went straight up to 100 kilometers and stopped, you would simply fall back down. You need the sideways velocity to continuously fall around the Earth rather than back to its surface. This is what an orbit actually is. It is not floating in space above the Earth, it is falling, constantly falling. The International Space Station is falling toward Earth every single second. But it is also moving sideways so fast that as it falls, the Earth curves away beneath it at exactly the same rate. So it never gets any closer to the ground. It just keeps falling and falling, forever circling the planet. This is not going up. This is going sideways so fast that down stops mattering. And this is a fundamentally different concept from what most people imagine when they think about going to space. So when you see that rocket launch and your brain says it is going up, it is actually doing something far more nuanced. It is gaining just enough altitude to get above the atmosphere where air resistance would slow it down, and then it is spending the vast majority of its fuel to accelerate sideways to build up enough horizontal velocity to enter orbit. The up part is almost a footnote. The real work, the real physics, is all about sideways speed, about going fast enough parallel to the ground that you enter a perpetual state of falling. And here is where the language we use betrays us. We say astronauts go up to space. We say the rocket went up. We say space is up there. But none of these statements are physically accurate. The astronauts went away from the centre of mass of the Earth. The rocket went perpendicular to the surface and then mostly parallel to it. And space is not up there, because there is no universal up to define where there is. Space is simply everywhere that is not inside a planet or star or other celestial body. It surrounds us in all directions. It is below the people in Australia. It is to the side of someone standing at the equator. The only reason we associate space with up is because we look upward from the Earth's surface and see it. But that is a perspective unique to our location. It is not a fact about space itself. Let me give you another way to think about this. Imagine you're an ant living on the surface of a basketball. To you, up is away from the surface of the basketball, and down is toward it. Now imagine there are millions of ants all over the basketball. Every single one of them points up in a different direction. There is no agreement. There is no universal up. There is only each ant's local experience of what direction takes them away from the surface they stand on. Now zoom out. Look at the basketball from the outside. From outside, there is no up or down at all. The basketball is just a sphere floating in space. The ant's individual concepts of up are purely local, purely relative, and completely meaningless from any external perspective. Earth is that basketball. We are those ants. And our concept of up is exactly as limited, exactly as local, and exactly as meaningless in the grand scheme of the cosmos. Now I want to take you deeper. We have established that up and down are local phenomena created by gravity and detected by our vestibular system. But now I want to show you something that will fundamentally change how you think about gravity itself. Because so far we have been talking as if gravity is a force that pulls things in a direction, and that direction happens to be what we call down. But this picture, this Newtonian picture of gravity as a force, is incomplete. It is an approximation. A very useful approximation for everyday life, but an approximation nonetheless. The real story of gravity, as told by Einstein's general theory of relativity, is far stranger and far more beautiful. In 1915, Albert Einstein published his general theory of relativity, and it completely overturned our understanding of gravity. Before Einstein, gravity was understood through Newton's framework. Newton said that every object with mass attracts every other object with mass. He gave us the equation: the force of gravity equals the gravitational constant times the product of two masses divided by the square of the distance between them. This works beautifully for almost everything in everyday life. It lets us calculate the orbits of planets, the trajectories of rockets, the weight of objects on a scale. But Newton himself admitted that his theory had a problem. It described what gravity does, but not what gravity is. It told you how to calculate the pull, but not how that pull was transmitted across empty space. Newton called this action at a distance and said he would frame no hypothesis about it. He knew something was missing. Einstein found what was missing, and the answer is astonishing. Gravity is not a force. Let me say that again because it is so counterintuitive that your brain will resist it. Gravity is not a force. Objects in a gravitational field are not being pulled by anything. They are not experiencing a force in the direction we call down. Instead, they are following the natural geometry of space-time itself. And that geometry is curved by the presence of mass and energy. Here is what this means in plain language. Imagine the universe is a four-dimensional fabric, 3 dimensions of space and 1 of time, all woven together into what physicists call space-time. In the absence of any matter or energy, this fabric is flat, perfectly, geometrically flat. In flat space-time, objects that are not being pushed or pulled by anything travel in straight lines. They move in what we call geodesics, the straightest possible paths through space-time. In flat space-time, a geodesic is what you would intuitively call a straight line. But now put a massive object like the Earth into this fabric. The mass of the Earth warps the fabric of space-time around it. It creates a curvature. And in curved space-time, geodesics are no longer straight lines in the intuitive sense. They are curved paths. They bend toward the source of the curvature. An object following a geodesic in the curved space-time around Earth will naturally move toward the Earth, not because it is being pulled, not because there is a force acting on it, but because the path it is following, the straightest possible path through the curved geometry of space-time, happens to lead toward Earth. Think about it this way. Imagine you are walking in what you believe is a perfectly straight line across what you believe is a flat surface. But what if the surface is actually curved? What if you are walking on the surface of a giant sphere without knowing it? You think you are going straight, but you are actually following the curvature of the sphere. An outside observer would see you curving, but from your perspective, you are doing nothing special. You are just walking straight ahead. This is exactly what gravity does to objects in space-time. They think they are travelling in a straight line. From their own reference frame, no force is acting on them, but the space-time they are moving through is curved, and so their natural straight-line path brings them closer to the source of that curvature. This is why Einstein said that gravity is geometry. It is not a force pulling things down. It is the shape of space-time telling things where to go. And when you sit in your chair right now, feeling the weight of your body pressing into the seat, feeling what you interpret as gravity pulling you down, what is actually happening is this. You are trying to follow a geodesic, a straight path through curved space-time that would take you toward the centre of the Earth. But the chair is in the way. The chair is pushing you away from that geodesic. The chair is accelerating you upward, away from the path you would naturally follow. The sensation you feel as weight, as gravity, is not the Earth pulling you down. It is the chair pushing you up. This is the most profound shift in perspective in the history of gravitational physics. You are not being pulled down, you are being pushed up. The ground beneath you is constantly accelerating you upward, away from the natural freefall trajectory you would follow if the ground were not there. A person in freefall, a skydiver before their parachute opens, an astronaut in orbit, They are the ones following the natural path through space-time. They are the ones experiencing no force at all. They are weightless, not because gravity has stopped working, but because they are finally following the geometry of space-time without anything pushing them off course. And this brings us to a startling conclusion. The direction we call down, the direction we feel gravity pulling us, is not a real force direction at all. It is the direction in which space-time is curved, and up, the opposite of down, is simply the direction in which the ground is accelerating us away from our natural geodesic. Up is not a real direction in space. It is the direction of resistance. It is the direction of the push that keeps us from falling. And in the absence of that push, in the absence of a surface or a rocket engine or anything else to resist freefall, there is no up and no down. There is only the geometry of space-time and the natural paths through it. This is not philosophy. This is not speculation. This is established, experimentally verified physics. And the experimental evidence is overwhelming. Let me tell you about one of the most elegant confirmations. In 1959, Robert Pound and Glenn Rebka performed an experiment at Harvard University that directly measured the predictions of general relativity about space-time curvature. They placed a gamma-ray emitter at the bottom of a 22-meter tower and a detector at the top. According to Einstein, time runs slightly slower in a gravitational field. Closer to the Earth, where space-time is more curved, clocks tick slower. Higher up, where space-time is less curved, clocks tick faster. This means that the frequency of light should shift as it moves up or down in a gravitational field. Light moving upward should be red-shifted, losing energy. Light moving downward should be blue-shifted, gaining energy. Pound and Rebka measured this shift, and it matched Einstein's prediction to extraordinary precision. Clocks at the bottom of the tower were indeed running slower than clocks at the top. Not because of any force, not because of any pull, but because space-time itself is curved around the Earth, and that curvature affects the flow of time. This experiment proved that what we call gravity is not a force at all. It is a geometric property of space-time, and every GPS satellite in orbit around Earth today provides ongoing confirmation of this fact. GPS satellites carry atomic clocks that tick faster than identical clocks on Earth's surface by about 38 microseconds per day, exactly as predicted by general relativity. If engineers did not account for this relativistic time dilation, GPS would accumulate errors of about 10 kilometers per day. The fact that your phone can tell you your location to within a few meters is living proof that space-time is curved and that gravity is geometry. So where does this leave us regarding the concept of up? It leaves us with a radical conclusion. Up is not a direction in the universe. It is a human interpretation of a local resistance to space-time curvature. When you feel up, what you are actually feeling is your body being pushed away from the geodesic it would naturally follow. You are feeling acceleration, not direction. You are feeling resistance, not orientation. And the moment you stop resisting, the moment you enter freefall, up disappears. Not because you cannot find it, but because it genuinely does not exist in your reference frame anymore. Now let us scale up and consider what happens as you move beyond Earth's gravitational influence entirely. Let us take the journey that no science class properly explains. You are in a spacecraft, and you have left Earth orbit. You are moving through interplanetary space, heading somewhere anywhere. The Sun is behind you. Jupiter is ahead. Earth is a pale blue dot receding in the distance. In which direction is up? You might instinctively say up is away from the Sun, perpendicular to the plane of the solar system. But why? Who decided that? The plane of the solar system, what we call the ecliptic plane, is defined by the orbit of the Earth around the Sun. But this plane is tilted about 60 degrees relative to the plane of our galaxy. So if you defined up as perpendicular to the galactic plane instead, you would get a completely different direction. And the galactic plane itself is arbitrarily oriented relative to other galaxies, which are arbitrarily oriented relative to galaxy clusters, which are arbitrarily oriented relative to the large-scale structure of the universe. There is no final reference. There is no ultimate up. There are only reference frames within reference frames within reference frames, each one arbitrary, each one chosen by convention, and none of them fundamental. In 1990, the Voyager 1 spacecraft, which had just completed its tour of the outer planets, was commanded to turn its camera around and take one final photograph of Earth. This was at the request of astronomer Carl Sagan. The resulting image shows Earth as a tiny pale blue dot, less than a single pixel in size, suspended in a beam of scattered sunlight. Sagan wrote beautifully about this image, noting that on that tiny speck, every human who ever lived out their lives, every king, every peasant, every saint, every sinner. Every concept of up and down, every direction, every orientation that any human has ever felt or imagined exists only on that imperceptible speck. Now, Voyager 1, as of the latest data, has travelled more than 24 billion kilometres from Earth. It is in interstellar space. It has left the Sun's magnetic influence. And if you asked which direction is up for Voyager 1, the question would be utterly meaningless. There is no gravitational field significant enough to define a local down. There is no surface to push it. There is no reference. Voyager 1 is simply moving through space in a particular direction, which we can describe using coordinates relative to the Sun, or relative to the galactic centre, or relative to the cosmic microwave background. But none of these is up. None of these is fundamental. They are all arbitrary choices of human mathematicians. And this is not just a problem of scale. It is not that up exists but becomes hard to define at large distances. It is that up is a purely local concept that depends entirely on being near a massive object and resisting the curvature of space-time caused by that object. Remove those conditions, and up is not merely undetermined, it is non-existent. It is like asking what temperature is the colour blue. The question contains a category error. It attempts to apply a concept in a domain where that concept has no meaning. Let us now consider something even more fascinating. Let us look at how professional physicists and astronomers actually navigate this lack of direction when they study and explore space. Because if up does not exist, how do we describe where things are? How does NASA tell a spacecraft where to go? How do astronomers point their telescopes? The answer is coordinate systems, and they are entirely artificial. In astronomy, there are multiple coordinate systems in common use, and they are all arbitrary human inventions. There is the equatorial coordinate system, which uses the Earth's equator projected onto the sky as its reference plane. There is the ecliptic coordinate system, which uses the plane of Earth's orbit around the Sun. There is the galactic coordinate system, which uses the plane of the Milky Way galaxy. There is the supergalactic coordinate system, which uses the plane of the local supercluster of galaxies. Each one defines up differently. Each one is useful for different purposes, and none of them represents any fundamental truth about which direction is actually up in the universe. They are tools, like rulers and clocks. Useful, necessary even, but not features of reality itself. They are features of our description of reality, which is a very different thing. NASA's mission planning uses various coordinate frames depending on the phase of a mission. Near Earth, they might use an Earth-centered frame. In transit between planets, they use a Sun-centered frame. Near the destination, they use a frame centered on that body. At each transition, up changes. Or rather, at each transition, the arbitrary reference shifts. The spacecraft does not feel any difference. The physics does not change. Only our description changes. only our human-imposed framework rotates. This brings us to one of the deepest insights of modern physics, one that took centuries to fully appreciate. The laws of physics do not depend on coordinates. They do not depend on which direction you call up or down or left or right. They do not depend on where you place the origin of your coordinate system or how you orient your axes. The laws of physics are, in the technical language, covariant. They have the same form regardless of how you choose to describe them. This is not just a convenience, it is a profound statement about the nature of reality. Reality does not care about our coordinates. Reality does not have preferred directions. Reality is isotropic, the same in all directions, at the most fundamental level. This isotropy is not just a theoretical assumption. It has been measured. The cosmic microwave background, the oldest light in the universe, emitted when the cosmos was only about 380,000 years old, is uniform to within 1 part in 100,000 in all directions. No matter which way you look, the universe looks essentially the same. There is no special direction. There is no cosmic up. The universe does not have a top or a bottom. It does not have a front or a back. It just is, in all directions equally. Now I want to take you somewhere even more profound. We have been talking about space on the large scale, on the scale of planets and stars and galaxies. But what about the very small scale? What happens to the concept of direction, the concept of position itself, when we zoom in to the quantum level? Because if you thought the absence of up in outer space was mind-bending, wait until you see what quantum mechanics does to the entire concept of location. In the early 20th century, physicists made a series of discoveries that shattered our classical understanding of how particles behave. At the scale of atoms and subatomic particles, the world does not work the way our everyday intuition suggests. Objects do not have definite positions until they are measured. They do not travel along well-defined paths. They exist in what physicists call superpositions, states of combined possibility where they are simultaneously in multiple places, moving in multiple directions, until an observation forces them to choose. In 1927, Werner Heisenberg formulated what became known as the uncertainty principle. This principle states that there is a fundamental limit to how precisely you can simultaneously know certain pairs of properties of a particle. The most famous pair is position and momentum. If you measure a particle's position with perfect precision, you must have complete ignorance of its momentum, which includes its direction of motion. If you know exactly where a particle is, you cannot know which way it is going. If you know exactly which way it is going, you cannot know where it is. This is not a limitation of our instruments. This is not about building better microscopes or more sensitive detectors. This is a fundamental feature of reality at the quantum level. The particle does not have a definite position and a definite direction simultaneously. These properties are not both real at the same time. The universe itself does not contain that information until a measurement brings one of them into existence. Think about what this means for our concept of direction. If a particle does not have a well-defined position, if it is smeared out across a region of space in a probability distribution, then asking which direction is up relative to that particle is even more meaningless than asking it in empty space. The particle does not have a location from which to define up. It is not anywhere specific. It is everywhere within its probability distribution simultaneously. Direction requires a reference point, a here from which to define the there. But quantum mechanics tells us that here is not definite. Here is fuzzy. Here is probabilistic. And therefore, direction is not just absent in the way it is absent in deep space. At the quantum level, direction is fundamentally undefined, because the very concept of position from which direction derives is itself indeterminate. Now, you might have heard the terms spin up and spin down in quantum mechanics, and you might wonder if these contradict what I am saying. After all, if quantum particles have a property called spin, and that spin can be up or down, does that not mean that up and down exist at the quantum level? This is a wonderful question, and the answer reveals how misleading our language can be. Quantum spin is not spinning. A particle with spin is not rotating like a top. And spin up does not mean the particle is oriented upward in any spatial direction. Spin is an intrinsic angular momentum that has no classical analogue. It is a purely quantum mechanical property. When we say a particle has spin up, what we actually mean is that when we measure its spin along a particular axis that we have chosen, the result is positive. But here is the crucial point. We choose the axis. We could measure along any axis we want, the x-axis, the y-axis, the z-axis, or any direction in between. The terms up and down in spin are arbitrary labels for the two possible measurement outcomes along whatever axis we happen to choose. They do not refer to any spatial direction. A spin-up electron measured along the vertical axis is not pointing toward the sky. It simply gave a positive result when its angular momentum was measured along the axis we arbitrarily labelled as the z-axis. In fact, quantum mechanics tells us something even stranger. Before you measure a particle's spin along any axis, the particle's spin can be in a superposition of up and down relative to that axis. It is both. Simultaneously, it does not have a definite direction of spin until you force it to choose by measuring it. And even then, the direction is only defined relative to your measurement apparatus, not relative to any universal up or down. So even in the quantum world, even in the language physicists use to describe the most fundamental constituents of matter, up and down are not real directions. They are labels. Conventions. Human choices about how to orient a measurement device. The universe at its smallest, most fundamental level has no preferred direction. No up, no down, no orientation. Just probabilities and superpositions and a magnificent mathematical structure that is completely directionless. Let us go even deeper. Let us talk about the fabric of space-time itself at the quantum level, because this is where our understanding reaches its current edge, and the implications are extraordinary. When we combine what we know from quantum mechanics with what we know from general relativity, we arrive at a picture of space-time that is almost incomprehensible in its strangeness. At very small scales, around 10 to the negative 35 meters, what physicists call the Planck length, space-time itself is thought to stop being smooth. At this scale, the effects of quantum uncertainty apply not just to particles within space-time, but to space-time itself. The geometry of space fluctuates. Distances become uncertain. The smooth fabric that Einstein described begins to foam and bubble with quantum fluctuations. This concept, often called quantum foam or space-time foam, was first proposed by John Archibald Wheeler in 1955. Wheeler suggested that at the Planck scale, space-time is not the calm, smooth manifold that general relativity describes. Instead, it is a roiling, turbulent froth where tiny regions of space are constantly forming and dissolving, where the very topology of space changes from moment to moment, where wormholes and tiny black holes flash in and out of existence faster than we could ever observe. Now think about what this means for direction. If space-time itself is fluctuating at the smallest scales, if the geometry of space is uncertain, then direction is not merely undefined in the way we discussed before. It is literally not a coherent concept at these scales. Direction presupposes a smooth geometry. You need a smooth, well-defined space to point in a direction within it. But if space itself is foaming and bubbling, if geometry is uncertain, then there is nothing stable for direction to refer to. Up, down, left, right, all directions dissolve into quantum indeterminacy at the Planck scale. The very framework within which direction could exist stops being reliable. We do not yet have a complete theory of quantum gravity. This is one of the great unsolved problems in physics. But all approaches to this problem, whether they come from string theory, loop quantum gravity, or other frameworks, agree on one thing: at the most fundamental level, space-time as we know it, it is not fundamental. It is emergent. It arises from something deeper, something that does not have the smooth geometric properties we associate with space. Some approaches suggest that space-time emerges from quantum entanglement. Others suggest it emerges from discrete units of geometry smaller than the Planck length. Still, others suggest it emerges from vibrations of one-dimensional strings in a higher dimensional space. In loop quantum gravity, for example, space is not continuous. It is made of discrete quanta. Think of it like a fabric that at a close enough magnification reveals individual threads. The volume of space comes in discrete chunks. Area comes in discrete quanta. There is a smallest possible length, a smallest possible area, a smallest possible volume. At this level of description, asking which direction is up is like asking which direction is up on an individual thread in a piece of cloth. The question does not apply. You need many threads woven together into a fabric before the concept of direction on that fabric becomes meaningful. Similarly, you need many quanta of geometry assembled together into a smooth spacetime before direction becomes a coherent concept. In string theory, the story is different in its details but similar in its implications. String theory posits that the fundamental constituents of reality are one-dimensional vibrating strings. These strings vibrate in a space with more than 3 spatial dimensions, typically 9 spatial dimensions plus 1 of time. The extra dimensions are thought to be compactified, curled up so small that we cannot observe them directly. In this picture, our 3-dimensional experience of space, including our concept of direction within that space, is a large-scale approximation of a much richer, higher dimensional reality. Up and down in our 3-dimensional space have no special status. They are artifacts of how the extra dimensions happen to be compactified. A different compactification would give a different 3-dimensional space, with different directions, different physics, even different forces. Our up is contingent, not fundamental. Both of these approaches, and others besides, point toward the same conclusion from different angles. Space as we experience it, with its 3 dimensions and its clear directions, is not the deepest level of reality. It is a macroscopic phenomenon that emerges from something more fundamental that does not have directions at all. Up does not exist at the bottom of reality. It only appears when you zoom out far enough for the quantum foam to average out into the smooth spacetime of general relativity. It only appears when enough geometry assembles to create something you can orient yourself within. And even then, it only appears locally, near massive objects, as a description of spacetime curvature. Let us now ascend from the quantum realm back to the cosmic scale, because there is one more devastating argument against the concept of up that comes from cosmology, and it is perhaps the most powerful of all. Consider the large-scale structure of the universe. When astronomers map the distribution of galaxies on the largest scales, they find something remarkable. Galaxies are not scattered randomly through space. They are organized into vast structures. Filaments of galaxies stretch across hundreds of millions of light-years. Between these filaments are enormous voids, nearly empty regions of space that can span hundreds of millions of light-years across. The filaments intersect at nodes where huge galaxy clusters sit. The whole thing looks, at the largest scale, like a cosmic web, a 3-dimensional network of matter threading through vast emptiness. But here is the key point. This cosmic web has no preferred orientation. There is no top to it. There is no bottom. No filament is more upward than another. No void is above or below another. The structure is, statistically, the same in every direction. This is the cosmological principle. On sufficiently large scales, the universe is homogeneous and isotropic. observations of the cosmic microwave background, of galaxy distributions, of the abundance of elements, all confirm this principle to high precision. The universe does not have a preferred direction. There is no cosmic up. You might ask, what about the Big Bang? Surely the Big Bang happened somewhere, and maybe up means away from that point? But this is another common misconception. The Big Bang did not happen at a specific location in space. It happened everywhere. Every point in the universe was once part of the Big Bang. The Big Bang was not an explosion outward from a central point into pre-existing space. It was an expansion of space itself. Every point moved away from every other point. There is no center. There is no edge. There is no point you could call the bottom from which everything expanded upward. The expansion is symmetric. It looks the same from every point, and since there is no center, there is no radial direction you could define as up or away. This is deeply counterintuitive, because every explosion we have ever witnessed in everyday life does have a center. When a bomb goes off, debris moves outward from a point. You can point toward the center and say that is where it came from, and away from the center is out, which we might call up. But the Big Bang is not like this. The Big Bang is the expansion of the metric itself, the expansion of the distances between all points simultaneously. Imagine an infinite sheet of rubber with dots painted on it, stretching uniformly in all directions. From the perspective of any dot, all other dots are moving away. No dot is the center, no direction is more away than another. This is our universe. And in such a universe, up is meaningless at the cosmic scale, just as it is meaningless at the quantum scale, just as it is meaningless in the depths of interplanetary or interstellar space. There is one more cosmological observation I want to share with you, because it drives this point home with extraordinary force. In 2013, the European Space Agency's Planck satellite produced the most detailed map ever made of the cosmic microwave background radiation. This radiation is the afterglow of the Big Bang, emitted about 380,000 years after the beginning of the universe, and it fills all of space uniformly. The Planck satellite measured the temperature of this radiation in every direction and found it to be the same to within about 1 part in 100,000. 2.725 Kelvin everywhere. In every direction, no matter where you look. If the universe had an up, if there were some preferred direction in the cosmos, we might expect to see some signature of it in this radiation. Perhaps it would be slightly hotter in one direction and cooler in another. Perhaps there would be a gradient. But there is not. The universe at this primordial level is stunningly uniform and directionless. There is no axis, there is no pole, there is no up. Now, scientists did find tiny fluctuations in the cosmic microwave background, variations of about 1 part in 100,000. These fluctuations are the seeds from which all cosmic structure grew, the primordial density variations that eventually became galaxies, clusters, and the cosmic web. But these fluctuations are random. They have no preferred direction, they are not aligned, they do not point anywhere. They are noise, beautiful and productive noise that gave rise to everything we see in the universe, but directionless noise nonetheless. So we have arrived at this comprehensive understanding, from the quantum foam at the smallest scale to the cosmic microwave background at the largest scale, from the surface of the Earth to the depths of interstellar space, from the inside of a rocket to the ergosphere of a black hole. There is no up. Up is a local, temporary, scale-dependent illusion created by the interaction of mass with space-time geometry and detected by biological organs that evolved for survival on a planetary surface. It is not a feature of reality. It is a feature of our experience of reality. And those are very different things. Now let me take you into perhaps the most mind-bending aspect of all this. Let us talk about what happens to the concept of direction near extreme gravitational objects, because this is where our intuition does not just break down, but completely inverts. Consider a black hole. A black hole is a region of space-time where gravity is so extreme that nothing, not even light, can escape once it crosses a boundary called the event horizon. In the classical picture, the event horizon is a surface of no return. Cross it, and you will inevitably reach the singularity at the centre, no matter what you do. But here is the truly incredible part. Inside a black hole, according to general relativity, the roles of space and time swap. Outside a black hole, you can move freely in space, going left or right, up or down, forward or backward. And time moves relentlessly forward, carrying you into the future whether you like it or not. But inside the event horizon, radial space, the direction toward the singularity, takes on the character of time. Moving toward the singularity is no longer a spatial direction. It becomes as inevitable and unidirectional as the flow of time. You cannot avoid it any more than you can avoid next Tuesday. And what was time outside becomes spatial in some sense inside. What does this mean for the concept of up? If you were falling into a black hole and you defined down as toward the singularity, then inside the event horizon, down is not a direction in space anymore. It is a direction in time. Down is the future. And up, if it means away from the singularity, is the past. And just as you cannot go back in time, you cannot go up inside a black hole. Going up becomes physically impossible in the most absolute sense imaginable. It is not that something is preventing you. It is that the geometry of spacetime itself has rearranged to make up a direction that does not exist in your available dimensions of movement. This is perhaps the most extreme example of how up is not a universal concept. In different regions of spacetime, under different gravitational conditions, the very meaning of spatial directions changes. What counts as a direction you can move in, what counts as inevitable, what counts as accessible, all of this depends on the local geometry of spacetime. And that geometry is different everywhere. Near Earth, it is mildly curved. Near a neutron star, it is strongly curved. Near a black hole, it is so curved that space and time lose their distinct identities. There is no universal framework of directions that applies everywhere. There cannot be, because the geometry that defines direction is different at every point. Let me now talk about something that brings all of these ideas together in a practical and experimentally verified way. Let us talk about reference frames and the relativity of simultaneity, because this provides the final nail in the coffin for any notion of absolute direction. In Einstein's special theory of relativity, published in 1905, he showed that there is no absolute state of rest. This is the principle of relativity. The laws of physics are the same in all inertial reference frames. An inertial reference frame is one that is moving at constant velocity, not accelerating. If you are in a sealed room moving at constant speed, no experiment you can do will tell you your speed. No experiment will tell you whether you are moving or stationary. These concepts, absolute motion and absolute rest, do not exist. Now this has immediate implications for direction. If there is no absolute rest, there is no absolute coordinate system. If there is no absolute coordinate system, there is no way to define an absolute direction. Up in your reference frame might correspond to some combination of up, forward and sideways in another reference frame moving relative to you. And at relativistic speeds, close to the speed of light, things get even more extreme. Lengths contract along the direction of motion. Time dilates. The geometry of space itself is different for different observers. What you call a purely spatial direction, someone else moving relative to you calls a mixture of space and time. This mixing of space and time at relativistic speeds means that even the distinction between a spatial direction and a temporal direction is not absolute. It depends on who is observing. For one observer, two events might be separated purely in space, at the same time but different locations. For another observer moving relative to the first, those same events are separated in both space and time, at different locations and different times. The spatial direction connecting them is different for each observer. There is no fact of the matter about which direction really connects them in space, because space itself is observer dependent. So not only does up not exist as a universal direction, but the very directions that do exist are relative. They depend on who is observing, how they are moving, and where they are in the gravitational landscape of the universe. There is no absolute space. There is no absolute time. There is only space-time, and even space-time's geometry depends on the distribution of matter and energy within it. Now I want to bring all of this together into a coherent picture and show you why this matters, not just as an abstract physics lesson, but as a fundamental insight into the nature of reality and our place within it. We have journeyed through multiple scales and multiple branches of physics today. We started with the simple observation that people on opposite sides of the Earth define up in opposite directions. We explored how our vestibular system creates the illusion of direction through the detection of acceleration. We saw how astronauts lose their sense of up in space and how their brains rewire to function without it. We explored how rockets do not actually go up, but instead go sideways to achieve orbit. We dove deep into general relativity and learned that gravity is not a force pulling things down, but rather the curvature of space-time that defines what down locally means. We saw that even this local definition of down is not absolute, but depends on your reference frame. We travelled to the cosmic scale and found no preferred direction in the universe at large, no cosmic up, no edge, no centre. We descended to the quantum scale and found that direction is not even definable where position itself is uncertain and space-time foams with fluctuations. We looked inside black holes, where the direction toward the singularity ceases to be a spatial direction at all and becomes temporal. And we saw how special relativity makes even the distinction between different spatial directions observer-dependent. At every scale, in every context, from every angle, the conclusion is the same. Up does not exist as a feature of physical reality. It is a useful fiction, created by evolution, maintained by biology, reinforced by language, and shattered by physics. The universe is directionless. It has no top, no bottom, no orientation, no right way up. It simply is. A vast, curved, dynamic space-time, full of matter and energy, evolving according to laws that neither know nor care about which way is up. And here is why I think this matters beyond just physics. Our language, our thinking, our metaphors are saturated with directionality that does not correspond to reality. We say things are looking up when they improve. We say someone is on top of the world when they succeed. We say things are going downhill when they get worse. We say heaven is above us and hell is below us. We construct social hierarchies where up means powerful and down means powerless. We build maps with north at the top and instinctively think of northern countries as above southern ones. All of these are linguistic and cultural artifacts of a species that evolved on a planet with gravity, developed an inner ear that detects acceleration, and then projected that biological experience onto the entire universe. But the universe does not share our bias. The universe is perfectly egalitarian in its directionlessness. No direction is better or worse, higher or lower, more important or less important. There is no cosmic hierarchy of position. There is just space, stretching in all directions equally, curved here and there by mass and energy, hosting galaxies and stars and planets and life, all of it on equal footing regardless of orientation. Now let me take you through one more profound connection that ties quantum mechanics to our cosmic understanding of direction. Because this is where things get truly elegant. 2 in quantum field theory, the most successful theory in all of physics in terms of predictive accuracy. Particles are not little balls bouncing around in space. They are excitations of quantum fields. An electron is not a tiny sphere sitting at a location. It is a ripple in the electron field, a field that permeates all of space uniformly. The photon is not a little bullet of light. It is a ripple in the electromagnetic field. Every particle we know of is a ripple in its corresponding field, and these fields fill all of space equally. And here is the key point. These fields have no preferred direction built into them. The electron field does not point up. The electromagnetic field does not have a top. The fields are isotropic, the same in all directions, unless acted upon by external influences that break that symmetry. Gravity breaks it locally, giving us a local sense of direction. A magnetic field breaks it locally, giving charged particles a preferred axis, but these are local breaking of an underlying symmetry. The fundamental laws, the fundamental fields, are directionless. This is related to a deep principle in physics called Noether's theorem, proven by mathematician Emmy Noether in 1918. This theorem states that every symmetry of the laws of physics corresponds to a conservation law. The fact that the laws of physics are the same regardless of your position in space corresponds to the conservation of momentum. The fact that the laws of physics are the same regardless of what time you measure them corresponds to the conservation of energy. And, critically for our discussion, the fact that the laws of physics are the same regardless of your orientation in space, regardless of which direction you call up, corresponds to the conservation of angular momentum. This last one is profound. The universe conserves angular momentum because it has no preferred direction. The absence of a cosmic up is not just an absence, a lack, a void. It is a symmetry, and from that symmetry flows one of the fundamental conservation laws of physics. The fact that there is no up is not just a curious observation. It is a deep structural feature of reality from which measurable, testable consequences flow. Angular momentum is conserved because the universe has rotational symmetry, because no direction is special, because there is no up. Every spinning top, every orbiting planet, every rotating galaxy is testimony to the fact that the universe does not have a preferred direction. This is one of the most beautiful connections in all of physics. The simple observation that there is no up, when formalized mathematically, leads directly to conservation of angular momentum, which explains why planets orbit, why galaxies spin, why figure skaters speed up when they pull their arms in, why gyroscopes resist tilting. The absence of up is not a gap in reality. It is one of reality's deepest symmetries, and from it flows a wealth of physical phenomena. Let us now consider how all this plays out practically in the exploration of space, because the rubber meets the road when humans actually try to navigate and orient themselves in this directionless void. When NASA designs a mission, one of the first things engineers must do is define an attitude control system for the spacecraft. Attitude in aerospace engineering refers to orientation, which way the spacecraft is pointing, and this is fundamentally a human choice. The spacecraft does not have a natural up. It does not settle into any preferred orientation the way a boat settles upright in water. In the absence of external torques, a spacecraft will maintain whatever orientation it has been placed in, spinning or not, pointed at whatever it was pointed at. There is no restoring force that pulls it into an upright position because there is no upright. Engineers must therefore artificially define up for the spacecraft. They do this by choosing reference directions. Often, one axis is defined as pointing toward Earth for communication purposes. Another axis might be defined by the direction to the Sun for solar power generation. A third is defined to complete the set. But these are entirely arbitrary engineering choices. A different mission would make different choices, and the spacecraft itself does not care. It has no preference. It would function exactly the same in any orientation. On the International Space Station, the choice of orientation is even more explicit and visible. The ISS has a designated ceiling and floor. They are labelled and colour-coded. Equipment is installed with a consistent orientation. All of this is for the benefit of the astronaut's psychology. Without a defined up and down, astronauts become disoriented and less productive. Their brains, still wired for a world with gravity, function better when given consistent visual cues about orientation. So NASA creates an artificial up using labels, lighting from the ceiling, and consistent equipment placement. But every astronaut knows this is fiction. If they float upside down relative to the designated ceiling, nothing about the physics changes. The air does not flow differently, the equipment does not malfunction, the universe does not object. Up on the ISS is a psychological crutch, not a physical reality. This has been documented extensively in research on human factors in spaceflight. Studies conducted on the ISS have shown that astronauts who orient themselves randomly in the station perform tasks slightly worse than those who maintain a consistent orientation relative to the station's designated ceiling and floor. This is not because of physics, it is because of psychology. Human brains work better when they have a consistent reference frame, even if that frame is completely artificial. We are so deeply wired for up and down that removing it causes measurable cognitive effects. But some astronauts, particularly those who spend long durations in space, 6 months or more, report something fascinating. They report that after enough time, the psychological need for up diminishes. Their brains adapt more completely. They become comfortable floating in any orientation. They stop noticing which way the ceiling is. They develop what some researchers have called a three-dimensional spatial awareness that does not rely on gravitational reference. They become, in a sense, more aligned with physical reality than we are here on Earth. They perceive space as it actually is, directionless, three-dimensionally symmetric, without inherent orientation. This is remarkable when you think about it. These astronauts are, through extended exposure to the physical truth about space, literally rewiring their brains to perceive reality more accurately. They are undoing millions of years of evolutionary programming. They are learning at a neurological level that up does not exist. And they come back to Earth slightly changed, slightly more aware of the arbitrary nature of the direction they once took for granted. Now let us explore one more fascinating angle on this topic. Let us talk about artificial gravity and what it reveals about the nature of up and down. In science fiction, we often see rotating space stations or spacecraft that create artificial gravity through centripetal force. The idea is simple. If you spin a cylindrical station around its axis, anything on the inner surface of the cylinder will feel pushed outward by the rotation. To someone standing on that inner surface, it feels like gravity. Down is away from the axis of rotation toward the outer rim. Up is toward the axis. But notice what has happened here. In this scenario, down is not toward any massive object. It is toward the rim of the station. It is in the direction of centripetal acceleration, and up is toward the center, toward the axis. If the station is oriented with its axis pointing toward the sun, then up inside the station is toward the sun. If it is oriented differently, up is in a different cosmic direction. And if you are on one side of the station and I am on the opposite side, my down point's in the opposite direction from your down, just like people on opposite sides of the Earth. This demonstrates once again that up and down are not directions in space. They are directions defined by acceleration. On Earth, the acceleration is gravitational, caused by the curvature of space-time. On a rotating station, the acceleration is centripetal, caused by the rotation. But in both cases, down simply means the direction of acceleration, and up simply means the opposite. Neither has any cosmic significance. Neither points anywhere special. Neither is a real direction in the universe at large. There is actually a beautiful real-world demonstration of this concept. In 1966, NASA conducted the Gemini 11 mission. during which astronauts connected their spacecraft to an Agena target vehicle with a 30-meter tether and set the pair spinning. This created a tiny amount of centripetal force, and the astronauts observed that small objects inside the capsule drifted slowly toward the outer wall. A new down had been created. Not by gravity, not by any massive object, simply by rotation. The direction of down was completely under the control of the spacecraft's orientation and spin rate. It could be changed at will. It could be stopped at will. It was entirely artificial, entirely local, and entirely without cosmic significance. Let me now take you on a journey through time and explore how humanity's understanding of direction has evolved through history, because this provides important context for understanding why the misconception of up is so deeply ingrained. For most of human history, the Earth was assumed to be flat. In a flat Earth model, up and down are absolute. Down is toward the flat surface, up is away from it. These directions are the same everywhere on the surface and never change. In this model, up really is a cosmic direction, an absolute arrow pointing away from the ground toward the heavens. And for millennia, this seemed obviously true. When the ancient Greeks discovered that the Earth is a sphere, beginning with Eratosthenes measuring its circumference around 240 BC, the concept of up became more complicated. On a sphere, up varies from point to point. But for many centuries, this did not disturb people's sense that up still existed in some absolute sense. The medieval cosmos placed the Earth at the centre and imagined celestial spheres rotating around it. Up was radially outward, toward the stars. It was still an absolute direction, even if it varied across the Earth's surface. Newton's revolution in the 17th century changed things further. Newton showed that gravity is universal, that the same force that pulls an apple to the ground keeps the moon in orbit. But he still conceived of gravity as a force in absolute space. Newton believed in absolute space and absolute time, a fixed background stage on which physics plays out. In Newton's universe, you could still define up as a direction in absolute space, even if the force of gravity varied from place to place. It was not until Einstein that absolute space was abolished entirely. Einstein showed that there is no fixed background. There is no absolute stage. Space and time are dynamic. They are part of the physics, not a container for it. They curve and warp and respond to matter. And in Einstein's universe, there is simply no way to define an absolute direction. Every direction is local, relative, dependent on your reference frame and the distribution of matter around you. Einstein completed the dissolution of up. After Einstein, up is not merely a local approximation, it is a relic, a concept that has no place in fundamental physics. But our intuition has not caught up with Einstein. Our language has not caught up. Our everyday experience has not caught up. We still feel up. We still talk about going up. We still instinctively think of space as up there. And this gap between our intuition and physical reality is, I think, one of the most fascinating aspects of being a scientifically aware human in the 21st century. We live in bodies that insist up is real, while our minds know it is not. We navigate a world where up works perfectly well as a practical concept, while knowing that it fails utterly as a description of reality beyond our thin atmospheric shell. This tension between intuition and reality is not unique to the concept of up. It pervades all of modern physics. Our intuition says time flows at a constant rate, but relativity shows it does not. Our intuition says objects have definite positions and velocities, but quantum mechanics shows they do not. Our intuition says effects follow causes in a clear chain, but quantum entanglement suggests correlations that defy simple causal explanation. In every case, the universe is stranger, more subtle, and more beautiful than our evolved intuitions suggest. And in every case, the path to understanding requires letting go of what feels obvious and following the mathematics and experiments wherever they lead. Let us now consider one final thought experiment that I think crystallizes everything we have discussed. Imagine you are in a sealed room, a perfect cube, with no windows, no instruments, no connection to the outside world. Inside this room, you feel your normal weight. You feel gravity pulling you toward the floor. You would naturally say that down is toward the floor and up is toward the ceiling. But can you be sure of that? Can you be sure that you are in a room on the surface of a planet? According to Einstein, you cannot. You might be on the surface of the Earth. Or you might be in a rocket accelerating upward at 9.8 meters per second squared in the depths of interstellar space. Or you might be on the surface of a planet that is more massive than Earth but smaller, giving the same surface gravity. Or you might be at a specific distance from a black hole where the gravitational acceleration at your location happens to match Earth's. There is no experiment you can do inside that room that will tell you which scenario is real. The equivalence principle guarantees this. Your experience of up and down tells you nothing about where you are in the universe, what is outside the room, or what is causing the acceleration you feel. This thought experiment, known as Einstein's elevator, demonstrates something remarkable. Up and down do not connect you to the outside universe. They tell you only about your local acceleration. They are purely local information. They reveal nothing about the cosmos at large, nothing about where you are, nothing about what direction you are facing relative to anything outside your immediate vicinity. Up is a local measurement, not a cosmic compass. And with this, I want to bring us to what I consider the most profound implication of everything we have discussed. If up does not exist in the universe at large, if it is purely a local artifact of acceleration and space-time curvature, then what does this tell us about our place in the cosmos? I think it tells us something both humbling and liberating. It tells us that we are not at a special place in the universe. There is no cosmic hierarchy of position. We are not above or below anything in any cosmic sense. The universe does not have a top where things are better and a bottom where things are worse. We are simply here, on a planet, in a solar system, in a galaxy, in a universe that extends in all directions equally, with no preference, no orientation, no judgment about which way is up. And this connects to a principle that has been guiding physics for centuries, the Copernican principle. The idea that we are not at a special place or time in the universe. Copernicus showed we are not at the centre of the solar system. Galileo showed the Earth moves. Astronomers showed our Sun is one ordinary star among hundreds of billions. Cosmologists showed our galaxy is one ordinary galaxy among trillions. And the absence of up is the final extension of this principle. Not only are we not at a special place, but there is no special direction that we can claim as up. We are not oriented in any special way. We are not facing the right way. There is no right way. This is, I think, one of the deepest insights that physics offers about the nature of reality. The universe is completely democratic in its geometry. Every point is equivalent to every other point. Every direction is equivalent to every other direction. There is no up, no down, no centre, no edge. There is just the magnificent, isotropic, homogeneous, expanding, evolving space-time of our cosmos, in which we happen to exist, on a small rocky planet orbiting an ordinary star, feeling a sensation we call up that is nothing more than the local curvature of space-time under our feet, resisted by the electromagnetic forces between the atoms of the ground and the atoms of our shoes. Now let us explore another dimension of this discussion that connects directly to some of the most cutting-edge research in physics today. Let us talk about how the concept of emergence relates to direction, because this is where modern physics is making some of its most exciting progress. In the last 2 decades, physicists have become increasingly interested in the idea that space-time itself might be emergent. That is, space-time might not be a fundamental feature of reality, but rather something that arises from more basic ingredients, the way temperature arises from the motion of molecules, or the way the hardness of a diamond arises from the arrangement of carbon atoms. Temperature is not a fundamental property of individual molecules, it is a property of large collections of molecules. Similarly, space-time might not be fundamental. It might be a property of something more basic, something that does not have spatial or temporal characteristics. This idea has been given significant support by research into the connection between quantum entanglement and geometry. In 2006, physicist Shinsei Ryu and Tadashi Takeyanagi discovered a remarkable mathematical relationship between quantum entanglement and the geometry of spacetime. They showed that in certain theoretical frameworks, the amount of entanglement between two regions of a quantum system is directly related to the geometry of the spacetime that connects them. More entanglement means more spacetime connecting them. Less entanglement means less. If you remove all the entanglement, the spacetime between them pinches off and they become disconnected. This suggests something extraordinary. It suggests that spacetime is woven together by quantum entanglement. The spatial connections between different regions of the universe might be nothing more than quantum correlations between underlying quantum degrees of freedom. Space might literally be made of entanglement. And if this is true, then direction, the ability to point from here to there through space, is also made of entanglement. Direction is not fundamental, it is emergent. It arises from the pattern of quantum correlations in whatever the universe is fundamentally made of. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a bold conjecture, sometimes called ER equals EPRA. They suggested that quantum entanglement, the correlation between distant particles, and Einstein-Rosen bridges, what we commonly call wormholes, are actually the same thing. Every pair of entangled particles is connected by a tiny wormhole, and the smooth spacetime we experience is nothing but a vast network of these quantum wormholes, connecting everything to everything else in a web of entanglement. If this is true, and it remains a conjecture, but one that has generated enormous theoretical support, then the very fabric of space, the thing within which directions exist, is itself a network of quantum connections. Up would not exist at the fundamental level, because space does not exist at the fundamental level. Both would be emergent, arising from the quantum architecture beneath. Let me bring this back down to something more tangible with a specific example. Consider a hologram. A hologram is a two-dimensional surface that encodes a three-dimensional image. When you look at a hologram, you see depth, you see three-dimensional structure. But the information is stored on a flat surface. In a very real sense, the third dimension of the holographic image is emergent. It arises from the pattern of information on the two-dimensional surface, but does not exist as a fundamental feature of the hologram. There is strong theoretical evidence, originating from the work of Gerhard Hooft and Leonard Susskind in the 1990s, that our universe works the same way. This is the holographic principle. It states that all the information needed to describe a region of space can be encoded on the boundary of that region, on a surface with one fewer dimension. The three-dimensional interior is in some sense a projection, an emergent description arising from information on a two-dimensional boundary. If this is true, and the theoretical evidence is compelling enough that it is taken very seriously by the physics community, then the three dimensions of space we experience, including every direction within them, are not fundamental. They are projections, they are emergent. They arise from something more basic that lives on a lower dimensional boundary. In such a picture, asking which direction is up is even more removed from fundamental reality than we previously thought. Not only is up a local artifact of acceleration, not only is it absent in the universe at large, Not only does it dissolve at the quantum scale, but the very spatial dimensions within which up could be defined might themselves be projections of something more fundamental. Up is an illusion within an illusion, a direction within a space that is itself emergent from something deeper, layer upon layer of not quite reality, with the truly fundamental description lying beneath all of them, in a realm that may not have spatial dimensions at all. This is breathtaking when you contemplate it fully. We feel so certain that up is real. We feel it in our bones, literally in the otoliths of our inner ears. And yet, peel back layer after layer of physical reality, and up dissolves at every level. At the cosmic level, there is no preferred direction. At the relativistic level, directions are observer dependent. At the quantum level, position itself is uncertain. At the Planck level, space-time foams and geometry fluctuates. And at the deepest theoretical level, space itself may be emergent, a holographic projection from something more fundamental. At no level, at no scale, in no framework, does up exist as a fundamental feature of reality. Let me now talk about something that many people find surprising when they first encounter it. The relationship between direction and symmetry breaking in physics. Because while the fundamental laws have no preferred direction, our everyday experience is full of apparent directions. The direction gravity pulls, the direction a magnetic field points, the direction of the electric field from a charged particle. How do these apparent directions arise from fundamentally directionless laws? The answer is symmetry breaking. The fundamental laws of physics are symmetric, they do not prefer any direction. But the solutions to those laws, the actual configurations that matter and energy take, often break that symmetry. Consider water. The laws governing water molecules are perfectly symmetric, they do not prefer any direction. But when water freezes into ice, the crystal structure picks out specific directions. The ice has axes, it has planes, it has preferred orientations. The symmetry of the underlying laws is broken by the specific configuration the system finds itself in. Gravity works the same way. The laws of general relativity do not prefer any direction. They are perfectly symmetric. But a specific solution, like a massive sphere, breaks that symmetry. The presence of the Earth creates a specific space-time geometry that distinguishes radially inward from radially outward. This is how down and up emerge. Not from the fundamental laws, which are directionless, but from the specific configuration of matter, which breaks the directional symmetry. This is a crucial distinction. The laws do not care about direction, but the stuff obeys the laws in ways that create local apparent directions. It is like the difference between the rules of chess, which do not prefer any direction on the board, and a specific chess position, which has pieces clustered in specific areas. The rules are symmetric, but any specific game is not. Our universe's laws are symmetric under rotation, but our specific neighbourhood, with a big massive Earth nearby, is not. The Earth breaks the rotational symmetry and creates a local down. And here is the beautiful thing. We can predict exactly how this symmetry will break, because we know the laws. We can predict that near any massive body, there will be a local sense of down toward that body. We can predict that away from all massive bodies, there will be no sense of direction. We can predict that in free fall the broken symmetry is restored and directionlessness returns. All of this follows directly from the symmetric laws plus the specific distribution of matter. Direction is not a feature of the universe's laws. It is a feature of the universe's current state, which is a much more contingent, less fundamental kind of thing. Let me give you one more example of symmetry breaking that relates directly to our topic. In the early universe, moments after the Big Bang, the temperature was so extreme that all the forces of nature were unified. The electromagnetic force, the weak nuclear force, and the strong nuclear force were all aspects of a single unified force. At this stage, there was a higher symmetry than we observe today. But as the universe cooled, these forces separated in events called phase transitions. Each phase transition broke some symmetry. The specific way the symmetry broke determined which particles got which masses, which forces have which strengths, and ultimately the structure of the matter that makes up you and me. This is relevant because some of these phase transitions may have broken spatial symmetries as well. In some theories, the 3 spatial dimensions we experience are not the total number of dimensions. There may be more, curled up too small to see. And the specific way those extra dimensions curled up, the specific symmetry breaking that occurred in the early universe, might be what gave us 3 large spatial dimensions rather than some other number. If this is correct, then the very existence of 3 dimensions to have directions in is contingent. It resulted from a phase transition. A different breaking of the symmetry would give a different number of large dimensions, different geometries, different possibilities for direction. This is highly speculative, I should say. We do not yet know if extra dimensions exist, or if the number of large dimensions is determined by a phase transition. But the theoretical frameworks that suggest this, primarily string theory, are taken seriously by many physicists, and the implication is striking. Not only does up not exist as a preferred direction within our 3-dimensional space, but the 3-dimensional space itself, with its possibility for 3 independent directions, may be a contingent accident of cosmic history rather than a fundamental feature of reality. Now I want to bring our discussion to a very concrete and experimentally grounded point. Let us talk about how the absence of preferred direction in the universe has been tested, verified, and utilized in real physics experiments. One of the most stringent tests of rotational symmetry, the symmetry that implies no preferred direction, comes from experiments looking for violations of Lorentz invariance. Lorentz invariance is the symmetry of special relativity. It states that the laws of physics are the same in all inertial reference frames, regardless of velocity or direction. If there were a preferred direction in the universe, a cosmic up, it would show up as a violation of Lorentz invariance. Physical processes would behave differently depending on which direction they were oriented relative to this cosmic axis. Physicists have tested this with extraordinary precision. The Hughes-Drever experiment, first performed in 1960 and repeated many times since with increasing precision, looks for any dependence of nuclear energy levels on the orientation of a nucleus relative to the stars. If there were a preferred direction in space, the energy of a nucleus should depend slightly on which way it is oriented. These experiments have found no such dependence, to a precision of better than 1 part in 10 to the 27th power. That is 27 decimal places of confirmed directionlessness. The universe, to this extraordinary precision, does not have a preferred direction. There is no cosmic up. Similarly, the Michelson-Morley experiment, first performed in 1887 and the granddaddy of all null results in physics, showed that the speed of light is the same in all directions. If space had a preferred direction, light might travel faster in that direction, like sound travelling faster with the wind. But it does not. Light moves at exactly the same speed in every direction, to the best precision we can measure. This was, in fact, one of the key experimental results that led Einstein to special relativity in the first place. More recently, analysis of light from distant gamma-ray bursts has tested Lorentz invariance at even higher energies. These observations have confirmed that even high-energy photons travel at the same speed regardless of direction, confirming rotational symmetry to scales approaching the Planck energy. The universe, from the lowest energies we can probe to very nearly the highest, maintains its directional democracy. No direction is special. No direction is preferred. There is no up. I want to address one more common misconception before we bring this discussion to its conclusion. Some people, when first confronted with the idea that up does not exist in space, respond by saying something like, well, there is a north in space. The North Star marks the direction of the North Celestial Pole. And since maps have north at the top, north is up, so up does exist in space. It is toward the North Star. This reasoning contains multiple errors, each of which is instructive to unpack. First, north is not up. North is a direction on the Earth's surface, perpendicular to the direction we call up. On Earth, north is horizontal, not vertical. Confusing north with up comes from the convention of putting north at the top of maps, but this is purely a convention. Old maps placed east at the top. Some maps place south at the top. The choice is arbitrary. Second, the North Celestial Pole is not a cosmic direction. It is defined by the direction that Earth's rotational axis happens to point. This direction changes over time due to precession. The Earth's axis wobbles like a spinning top, tracing a circle on the sky over about 26,000 years. Polaris, the North Star, will not always be near the North Celestial Pole. In about 12,000 years, Vega will be the closest bright star to the pole. The direction we call north in the sky is temporary and parochial, defined by the current orientation of one planet in one solar system. It has no cosmic significance whatsoever. Third, even if we fixed a direction in space and called it north or up, this would be a label, not a physical thing. We can label any direction we want. We can call the direction toward the Andromeda Galaxy up if we choose. But labeling a direction does not make it special. The laws of physics would not distinguish it. No experiment would detect it. It would be a coordinate choice, no different from choosing where to put the zero on a ruler. Useful for communication, but devoid of physical content. Let me now bring us back to our opening story, back to Eugene Cernan floating in his spacecraft, staring at Earth with no sense of up or down. I want you to understand now, with all the physics we have covered, what he was experiencing at that moment. He was not confused. He was not disoriented in the way you are disoriented when you spin around and get dizzy. He was experiencing physical reality as it actually is. He was, for perhaps the first time in his life, free from the illusion of up. His vestibular system had nothing to detect. His eyes showed him no consistent floor or ceiling. The universe presented itself to him without the comforting fiction of direction. And in that moment, he was experiencing what the equations of physics have been telling us for over a century. There is no up. There never was. There is only the local, temporary, biologically generated sense of up that we carry with us like a security blanket, a relic of our evolutionary past on a gravitational planet. Now I want to take you into an area that very few people think about when discussing the direction problem in space. Let us talk about the arrow of time and how it relates to spatial direction, because this connection reveals something deep about the asymmetry we observe in our universe. We have established that spatial directions are symmetric. The laws of physics do not prefer left over right, up over down, forward over backward. This spatial symmetry is very well established experimentally. But time is different. Time appears to have a direction. Things happen in a particular order. Eggs break but do not unbreak. Coffee cools but does not spontaneously heat up. We remember the past but not the future. This asymmetry, called the arrow of time, is one of the great mysteries of physics. Why do I bring this up in a discussion about spatial direction? Because it highlights an important contrast. Space is symmetric, time is not. And yet, in general relativity, space and time are unified into space-time. They are different aspects of the same four-dimensional fabric. So how can space be directionless while time has a clear direction? This is a deep question, and the answer involves thermodynamics, the Big Bang, and the concept of entropy. The arrow of time arises because the universe began in a state of extraordinarily low entropy. At the Big Bang, or more precisely in the moments just after it, the universe was in a remarkably ordered, uniform state. The second law of thermodynamics tells us that entropy, roughly speaking the disorder or randomness of a system, tends to increase over time. Starting from that initial low entropy state, the universe has been evolving toward higher entropy ever since. This gives time its direction. The future is the direction of increasing entropy. But notice something crucial. This arrow of time does not come from the fundamental laws. The fundamental laws of physics, with very minor exceptions involving certain exotic particle interactions, are time symmetric. They work equally well forward and backward. The arrow of time comes from the initial conditions, from the low entropy state of the early universe. It is, in a sense, a broken symmetry, just as local gravity is a broken spatial symmetry. The laws do not prefer a direction of time. But the specific configuration of the universe, its very special initial state, creates one. And here is the deep connection. The spatial directionlessness of the universe is maintained because there is no corresponding spatial boundary condition. There is no low entropy edge of space that would create a preferred spatial direction, the way the low entropy beginning creates a preferred temporal direction. The Big Bang creates a temporal asymmetry, but no spatial asymmetry. This is why the cosmic microwave background is isotropic. This is why the cosmological principle holds. This is why there is no up. If hypothetically the universe had a special edge or boundary in some spatial direction, with very different conditions on one side compared to the other, we might have a spatial analogue of the arrow of time, a spatial arrow, a cosmic up. But we do not. As far as we can tell, the universe extends in all spatial directions equivalently. There is no edge, no boundary, no wall, no limit in any direction that we can detect. And therefore, there is no spatial asymmetry, no arrow of space, no preferred direction, no up. This connects to a truly mind-bending possibility in theoretical cosmology. Some cosmologists have proposed models in which the arrow of time is not fundamental either. In these models, there might be regions of the universe, or other cosmological epochs, where time runs in what we would call the backward direction. In such regions, entropy decreases with time from our perspective, eggs unbreak, memories of the future rather than the past exist, and everything flows in reverse. If this is true, and it is highly speculative but not in conflict with known laws, then even the one direction that seems special in our experience, the direction of time, might be local and contingent rather than universal and fundamental. And if time's arrow can be local, how much more so the spatial arrow we call up, which we have already shown to be local in every framework we have examined. Let us now explore a fascinating connection between the absence of up and the behaviour of light, because light's behaviour provides some of the most elegant confirmations of universal directionlessness. Light, as described by Maxwell's equations of electromagnetism, propagates as an electromagnetic wave. This wave consists of oscillating electric and magnetic fields, perpendicular to each other and to the direction of travel. Now here is something remarkable. When light is emitted from a source, it does not prefer any direction. A hot, glowing object emits light equally in all directions. A star radiates uniformly in 3 dimensions. An excited atom can emit a photon in any direction with equal probability. Light itself has no preference for up or down. When light travels through the vacuum of space, it follows geodesics of the space-time geometry, just like massive objects do. Near massive bodies, light curves. This is gravitational lensing, one of the most dramatic confirmations of general relativity. Light from distant galaxies passing near closer massive clusters of galaxies is bent by the curvature of space-time around those clusters. It does not bend in any preferred direction. It bends toward the mass, whatever direction that happens to be. The bending is determined entirely by the local geometry of space-time, not by any cosmic reference frame. In 1919, Arthur Eddington led an expedition to observe a total solar eclipse and measure the bending of starlight by the sun. He found that stars near the edge of the sun during the eclipse appeared shifted from their usual positions by an amount that matched Einstein's prediction from general relativity. The light was following the curved space-time around the sun, bending toward it. Not down. Not in any preferred direction. Just toward the local source of curvature. This experiment made Einstein world famous and confirmed that even light, the fastest thing in the universe, does not travel in absolute straight lines through absolute space. It follows the geometry of space-time, which is locally curved by matter and globally without preference. Gravitational lensing has since become one of the most powerful tools in astronomy. By observing how light from distant galaxies is distorted as it passes through galaxy clusters, astronomers can map the distribution of matter, including invisible dark matter, in those clusters. The patterns of distortion are complex and beautiful, arcs and rings and multiple images of the same distant source, but they have no preferred direction. The lensing occurs equally in all directions around the cluster because the cluster's gravity does not prefer any direction. It is spherically or elliptically symmetric, pulling spacetime inward from all sides equally. In 1998, observations of distant Type I supernovae led to the discovery that the expansion of the universe is accelerating. This was one of the most surprising discoveries in the history of cosmology. It implies the existence of something called dark energy, a form of energy that permeates all of space and drives the expansion to speed up over time. The distribution of dark energy, as far as we can tell, is perfectly uniform throughout space. It has the same density everywhere and in every direction. It contributes to the expansion equally in all directions. Even the mysterious force driving the cosmos apart does not prefer a direction. Even dark energy has no up. Now let us consider something I find deeply fascinating: the concept of direction in curved space versus flat space. We have been talking about direction as if it is straightforward, as if you can simply point and say that is a direction. But in curved space-time, even the concept of direction is more subtle than you might think. In flat space, you can compare directions at different points. If I am pointing north and you are 10 meters away pointing north, we are pointing in the same direction. This seems obvious. But in curved space, it is not true. In curved space, you cannot unambiguously compare directions at different points. This is because the curvature means that the result of moving a direction vector from one point to another depends on the path you take. This is called the path dependence of parallel transport, and it is one of the defining features of curved space. Here is an intuitive example. Imagine you are standing at the North Pole of the Earth, facing toward New York City. Now walk to New York City while always facing forward. You are now facing south. Now walk along the equator to a point in Africa while still facing forward. Now walk back up to the North Pole while still facing forward. When you arrive back at the North Pole, you will be facing a different direction than when you started, even though at every step you walked straight ahead without turning. The curvature of the Earth's surface rotated your direction of travel just by moving you around a closed loop. This is called holonomy, and it happens whenever space is curved. In the curved spacetime of general relativity, this effect applies to all direction vectors. If you try to transport a definition of up from one place to another, the result depends on what path you take. Two different paths will give you two different final directions. This means you literally cannot define a consistent global up, even if you wanted to. Even if you said, let me pick a direction and call it up for the whole universe, you would find that it is impossible to extend that definition consistently across a curved spacetime. The curvature prevents it. The geometry itself forbids a global direction. This is not an obscure mathematical technicality. This is a fundamental feature of our universe. Our universe has curved spacetime everywhere there is matter and energy, which is everywhere. And in this curved spacetime, global directions are impossible. You can define local directions just fine. At any single point, you can point in any direction you want. But you cannot extend that pointing consistently to other points without the curvature introducing ambiguity. Direction is irreducibly local, and since up is a direction, up is irreducibly local. Let me now discuss something that connects our topic to practical technology in a way that might surprise you. Gyroscopes. A gyroscope is a spinning wheel that resists changes to its orientation. Once spinning, it maintains its axis of rotation regardless of how you move the frame around it. Gyroscopes are used in navigation systems, in spacecraft attitude control, in aircraft instruments, and in many other applications. They work because of conservation of angular momentum, which, as we discussed earlier, is a consequence of the universe's rotational symmetry, its lack of preferred direction. But here is what is fascinating about gyroscopes in the context of curved spacetime. In flat space, a perfect gyroscope would maintain its orientation forever, always pointing in the same direction. But in curved spacetime, something remarkable happens. The curvature of space causes the gyroscope's axis to precess, to slowly rotate, even without any force applied to it. This is called geodetic precession, or de Sitter precession. It occurs because the curved spacetime parallel transports the gyroscope's spin axis along its orbit, and as we discussed, parallel transport in curved space can change directions. This effect was predicted by general relativity and has been measured. In 2004 to 2005, NASA's Gravity Probe B mission carried 4 ultra-precise gyroscopes in orbit around Earth and measured their precession. The results confirmed Einstein's predictions to high accuracy. The gyroscopes precessed by about 6.6 arcseconds per year due to geodetic precession, and about 0.039 arcseconds per year due to an additional effect called frame dragging, where the rotation of the Earth literally drags spacetime around with it. This is extraordinary. A gyroscope in orbit, pointing in what it considers a fixed direction, is actually slowly changing that direction, because spacetime itself is curved around the Earth. The gyroscope thinks it is pointing the same way. From its own local perspective, it is not turning. But from the perspective of distant stars, it is slowly precessing. This demonstrates beautifully that direction in curved spacetime is not absolute. Even a device specifically designed to maintain a fixed direction cannot do so in a curved geometry. Spacetime will not allow it. And frame dragging is even more remarkable. The rotation of the Earth drags spacetime around its axis, like a spinning ball in honey dragging the honey around with it. This means that the very directions in space near a rotating massive body are being twisted by the body's rotation. If you defined up as toward Polaris and stood near a massive rapidly rotating object, the frame dragging would literally twist your local up away from Polaris over time. The spacetime around the rotating body has been dragged, and with it, all local directions. This effect is tiny near Earth. But near rapidly rotating massive objects like neutron stars or the ergosphere of a rotating black hole, frame dragging can be enormous. In the ergosphere of a rotating black hole, frame dragging is so extreme that it is impossible to remain stationary. Space itself is being dragged around the black hole faster than the speed of light relative to distant observers. Any definition of direction in this region is being rotated continuously by the spacetime itself. Up does not just fail to exist in such a place, it would be actively destroyed by the rotation of spacetime even if you tried to define it. Now I want to share with you a thought that I find deeply beautiful. It comes from considering the totality of everything we have discussed and asking, if direction is not fundamental, if up does not exist, if space may be emergent, then what is fundamental? What is real at the deepest level?